Hey, welcome to round two on the immune system. Last time we were talking about macrophages and the fact you could have fixed macrophages like the Kupffer cells in the liver, or free macrophages like the dust cells in the lungs that are wandering around. So macrophages, of course, do phagocytosis. And in phagocytosis, what happens is the macrophage will detect the presence of a microbe. The macrophages will stick out these false arms called pseudopods. The tips of the pseudopods here connect to one another, engulfing the microbe or whatever it might be in a little bag called a phagosome. The phagosome fuses with a lysosome, an organelle that contains digestive enzymes. Upon combining, we have a phagolysosome, and the enzymes will destroy the microbe, leaving bits and pieces that might be expelled or might be put to another use, as we shall see as we proceed. Okay, here's the thing about macrophages, though. They're blind and they're dumb. So the odds of phagocytosis aren't great. I mean, the macrophage has to bump into the foreign thing almost perfectly. Luckily, of course, we can enhance that. If a microbe has been grabbed onto already by something called complement proteins, or by antibodies for that matter, that binding of complement or antibodies to a microbe will enhance the likelihood of phagocytosis. This process is called opsonization, which literally means, and I'm kind of translating a little roughly here, literally means to make tasty. So it's like the complement is seasoning the microbe, making it more delicious for the macrophage to engulf. All right, no messing around. Today's a fast day. We're going to fly today. There's another type of innate cell we have to be aware of, the natural killer cells. They're a specialized type of lymphocyte. Their thing is they attack and kill cells that have become infected with viruses or cancer cells. And here's a tumor cell right here. So tumor cells, cancer cells, are going to often display weird-looking alien proteins on their surface. Natural killer cells will say, I don't recognize those proteins. Better kill you. Meanwhile, if a virus takes over a cell, the virus is going to hijack that cell and force it to make viral proteins. If the natural killer cell sees a body cell with viral proteins on its surface, it knows it's infected and says, I'm going to kill you. Natural killer cell doesn't care who the virus is or what type of tumor, what type of cancer we're dealing with. It'll kill them all in the same manner. Natural killer cells, one of the neat things they do is they'll convince infected cells to kill themselves. So they'll induce cellular suicide in infected cells. Which is kind of cool. All right, cells are done. Now we got these special proteins called interferons. Interferons are proteins released by cells that have become infected with a virus. And what these guys will do in an altruistic fashion is interferons will diffuse to neighboring cells. So here's our infected cell, infected by a virus. It's making interferons. Interferons are going to diffuse to its neighbors who are still normal, and it'll convince the neighbors to start making enzymes and inhibit viral replication. And what this does is this decreases the ability of the virus to spread to other cells, cause other cellular and tissue damage, in other words, and also it is going to prevent these other cells from acting as virus factories, which is going to decrease the numerical spread of our viruses as well. Meanwhile, interferons attract macrophages, which can kill infected cells and also just eat up naked viruses. Interferons are going to attract natural killer cells, which will convince infected cells to commit cellular suicide, which, by the way, has the cool name of apoptosis. All right, so those are interferons. Complement system is another set of chemicals that we must be aware of. It's a group of about 20 or 30 or so plasma proteins made by the liver. It's always the liver, you know that. Now, these proteins are floating around in your plasma, mostly in an inactive state, and they're going to be activated. Can be activated by interacting with the surface of a microbe or by interacting with antibodies that have been activated already. Here is the pathway of complement activation schemes. Let me know if you want me to test you on this pathway. So, bottom line is complement set of proteins, immune proteins in your blood, pathogens, microbes, foreign things, turn them on. So question is then, what do the turned on complement proteins do? And the effect of activated complement can be summed up in one mnemonic device, the word COIL. C-O-I-L. The C stands for chemotaxis. Chemotaxis is the movement of white blood cells towards a chemical. So activated complement is going to attract white blood cells, which is good because complement is going to be activated by bacteria. So by attracting white blood cells to the complement, you're in effect attracting them towards the bacteria. Complement also is involved in opsonization. We mentioned this earlier. Complement proteins bind to a microbe. They make it tastier for a macrophage. They enhance the likelihood of phagocytosis, and that is known as opsonization. The I in COIL is inflammation. So activated complement proteins will bind to this guy, a basophil, and they'll cause the basophil to release histamine and heparin, which of course will cause local vasodilation. Local resistance goes down, blood flow goes up, capillary permeability goes up too. That results in inflammation. We'll deal more with inflammation momentarily. Last but not least, the L in COIL, the last effect of activated complement. L stands for lysis, which is the bursting of cells. And in this case, what some of the complement proteins do in response to being activated on the bacterial surface lipopolysaccharide, the complement proteins will assemble into this little tube-like thing, little donut, called a membrane attack complex. And the membrane attack complex pokes a hole in the bacterial cell membrane. That allows sodium, of course. Remember, sodium is abundant in your interstitial fluid. Sodium rushes in, osmotically dragging water with it, causing the cell to swell and swell and swell and burst or explode. Okay, complement done. Two processes. Inflammation, which we just mentioned in discussing complement. Inflammation occurs whenever tissues are damaged. Benefits include preventing the spread of pathogens, disposing of dead cells, damaged cells, bacterial cells, and also setting the stage for repair. Inflammation gets a bad rap. Inflammation is a good thing 99% of the time. It's just when it happens inappropriately, when it persists too long, that's when it is bad. 4 classic signs. Heat, hotness to the touch. Those are actually the same thing, aren't they? Heat, hotness to the touch, that's 1. Redness, that's 2. That's where the word inflammation, on fire, comes from. Then we got swelling, painfulness as well. All right, cells that release inflammatory chemicals, besides bacteria, activated white blood cells, and surface cells. Cells lining your trachea, for example. Cells lining your oral cavity, for example. Skin as well. Any place you're going to encounter bad things, any place that you're going to get cells damaged. All right. When you damage cells, membrane phospholipids are going to break. There's going to be a couple steps. We end up making a lot of, what's the word I'm looking for here? Inflammatory chemicals. Prostaglandins, prostacyclin, thromboxans, leukotrienes. And these guys are all going to act as chemotactic factors. They're especially the leukotrienes. They're going to cause bronchospasm, make your airways get a little narrower. They're going to increase your capillary permeability, vasodilation, cause fever. These are all good. They're all going to help you heal. But some of you don't like those symptoms. You may take drugs that inhibit these enzymes, COX and LOX. It's nice that they rhyme. These are 2 enzymes very much involved in the production of inflammatory chemicals. So tissue inflammation, swelling, pain, fever.